We've seen something about how to set up triple integrals and what they mean. We've encountered the integral that we show here, which is just the integral over the unit sphere centered at the origin of the volume increment. So this integral is going to give us the volume of the first octant of that unit sphere. Now, before we get into this, we're going to look at a very common and standard integration technique that you might be a little rusty on. You encountered this in first semester calculus or first year calculus when we did trigonometric substitutions. We're going to take advantage of the fact that 1 minus the cosine squared of theta equals sine squared theta, or that 1 minus sine squared theta equals cosine squared theta, and make a trigonometric substitution that'll give us one of those forms. The substitution is going to be, well, we're going to let x equal a, could be either the cosine or the sine of theta. There are advantages both ways. We'll just choose a cosine theta. The reason for that, of course, is then that a squared minus x squared becomes a squared minus a squared cosine squared theta. Factoring out the a squared, we get 1 minus sine squared theta, cosine squared theta, which is, excuse me, which is the square root of sine squared of theta, just giving us a sine theta to integrate. Now there'll be a little bit more to that, but let's see what happens here. Okay, so if x equals a cosine theta, then dx equals what? Well, it's going to be negative a sine theta d theta. So that this integral becomes the square root of, well, the integral of the square root of a squared minus a squared cosine squared theta times dx, which is negative a sine theta, running out of paper, d theta. And simplifying this, we can factor out the negative a here, and we can also factor a squared from within the square root, giving us another factor of a. We end up with negative a squared times the integral of the square root of 1 minus cosine squared theta times sine theta d theta, which then equals negative a squared times the integral. The square root of 1 minus cosine, well, 1 minus cosine squared theta is the sine of theta, so sine squared of theta, so the square root of that is going to give us just a sine theta times sine theta d theta, so we have negative a squared times the integral of sine squared theta d theta. There's more work to do to get this back into a form involving x, but we're going to leave it at this for right now, and we'll come along and look at how to deal with this form. It's simply a matter of integrating sine squared of theta with respect to theta, and there are two ways to do that. We can integrate by parts, or we can use a trigonometric substitution, not a substitution, but a trigonometric identity. And once more, this should be a technique that's familiar to you. So I want to move on to this expression. In this case, we're going to treat the 1 minus y squared as if it was an a squared and essentially do the same thing. So treat 1 minus y squared as a squared, meaning that we're going to let x equal a cosine theta. Now, if 1 minus y squared is a squared, then x is going to be square root of 1 minus y squared cosine theta, so that dx equals the square root of 1 minus y squared sine theta d theta, and following steps analogous to the steps that we see up here, we find that our integral, don't think I'm going to have room to write it here, but let's do the best we can. Our integral is going to be basically negative a squared times the sine squared of theta. Well, negative a squared in this case would be the negative square of 1 minus y squared. So we get negative 1 minus y squared times the integral of sine squared theta d theta. The only difference being that here we've got the familiar a squared minus x squared. Here we've got a 1 minus y squared minus x squared, and we're going to have to treat that 1 minus y squared as if it's an a squared, following very similar steps. In both cases, we have to integrate sine squared theta d theta. The integral sine squared theta d theta is obtained by, can be obtained by integration by parts. Let u equal sine theta, so that du equals cosine theta d theta. Let dv equal sine theta d theta, so that v equals the negative of the cosine of theta. The integral becomes uv, which is negative sine theta cosine theta, minus the integral of v du. Now, the v is negative cosine theta, so we're going to put the cosine theta here, factor out the negative, and that's going to make this positive. And then the v du is then going to be, the du is going to be cosine theta d theta, so that the integral of sine squared theta d theta equals negative sine theta cosine theta plus the integral of cosine squared theta d theta. Now, cosine squared theta is just 1 minus sine squared theta, so that's negative sine theta cosine theta plus the integral of 1 minus sine squared theta d theta. And this can be split into the integral of 1 times d theta minus the integral of sine squared theta d theta. The minus integral of sine squared theta d theta allows us to add the integral of sine squared theta d theta to both sides, obtaining 2 times the integral of sine squared theta d theta equals negative sine theta cosine theta plus the integral of just 1 d theta, which is just the integral of d theta, so that this side becomes negative sine theta cosine theta plus theta. Then we conclude that the integral of sine squared theta d theta is 1/2 of this. So that's negative 1/2 sine theta cosine theta plus theta over 2. I'm not going to go through it here, but if you take the derivative of this expression using the product rule here and so forth, you'll find that the derivative of this expression is indeed sine squared of theta. So now we can continue our integration of each of these expressions. Negative a squared times the integral sine squared theta d theta then is equal to negative a squared times negative 1/2 sine theta cosine theta plus theta over 2, which equals a squared, well, let's put the 1/2 out here, 1/2 a squared times sine theta cosine theta plus theta. Now x equals a cosine theta, so that cosine theta equals x over a. So we're going to have a sine theta times x over a. Sine theta is 1 minus cosine squared theta, so what we end up with here is the square root of 1 minus x squared over a squared. Remember again, x over a is the cosine of theta, so the sine of theta is the square root of 1 minus cosine squared theta equal to this expression, times x over a plus theta. If x equals a cosine theta, then cosine theta equals x over a, and theta itself is inverse cosine of x over a. Now, simple algebraic rearrangement that I'm not going to do in detail, but of course a divides the a squared, leaving us with just a. We can also put the expression here over the common denominator, a squared, under the square root, and then factor out the a squared from the denominator, getting rid of the other a. What we're left with is then 1/2 times the quantity x square root of 1 minus x squared plus the inverse cosine of x over a. Now the integral we get here is a very similar form. I'm not going to go through the details, but everywhere a has appeared here, square root of 1 minus y squared is going to appear in this integral, so that this integral will come over here and give us, but what we're going to end up with is, again, 1/2 x times the square root of 1 minus x squared. The only real difference is that we're going to have the inverse cosine of x over square root of 1 minus y squared. Now, having reviewed what we learned in first year calculus and maybe applied it to a situation where a is something besides just a number, we should be ready to go on and perform this triple integral, and we'll do that in the next clip.